Hello friends, welcome. We are dealing with the experiments related to operational amplifier and linear ICs. Today we will be discussing about inverting and non-inverting mode operation of an operational amplifier. You can see in the figure that pin number 2, that is the inverting input terminal, is connected to the input through the resistance Rin, whereas pin number 3, that is non-inverting input terminal, is grounded. At pin number 6 and pin number 2, one resistance is connected. We call it as feedback resistance RF. As the input is connected to the inverting input terminal, the output waveform, whatever we are getting, it will be 180 degree out of a phase that with respect to the input. How to calculate the output voltage? So V0 will be equal to gain times the input. So gain of the inverting input terminal will be two resistances, that is the output feedback resistance divided by the input resistance. Because of the 180 degree phase shift, we will use the negative sign for it. So gain of an inverting amplifier will be minus RF by Rin. By making use of this RF by Rin, we will choose the values of feedback resistance as well as input resistance depending on our application. Say for example, if I need a gain of 1, so Rin and RF will be same, so that RF by Rin will be equal to 1. Say I need 10 gain, then the RF value will be 10 times more than the resistance Rin, and so on. Now in this experiment, we are connecting the input to the inverting input terminal. We will apply the frequency through some signal generator, and for number of frequencies we will note down what is the output voltage. We will calculate the voltage gain, that is V out by V in. Then we will convert it to the in terms of decibels, and we will plot it on the semilog paper, and we call it as a frequency response of an inverting inverting amplifier. So first we will note down the frequencies, different frequencies, say 10 Hz, 20 Hz, 100, 500, 1K, 2K, 3K. We will go on checking what is the frequency value. At that we will check what is the output voltage. Then we will calculate the gain, that is V out by V in, and we will convert this gain into decibel, AV in decibel. So with this value, the gain in decibels, we can easily plot the frequency versus gain, and that we call it as the frequency response. Similarly, the other circuit, that is the non-inverting mode of operation of an op-amp, can be seen here. In the figure you can see the input is connected at the non-inverting input terminal, whereas the inverting input terminal is connected to ground through the input resistance Ri. Similarly, as we discussed previously, the output voltage is same as that of previous, so it will be gain times V in, but gain in the non-inverting input case, you just substitute it and you will get 1 plus RF by Ri. So gain will be not only minus RF by Ri, that is in the previous case inverting mode. Here it will be 1 plus RF by Ri. I have not used negative sign here. In the non-inverting mode, it is connected to non-inverting input terminal, input is connected. So the output is in phase with the input, or you can say the phase shift between output and input is 0 degrees. We call these signals as in phase signals. Again you can see the output is depending on the values of RF and Ri. Here also we'll make use of a signal generator. We'll set some voltage and frequency. For different frequencies, we'll note down the output voltage. We'll calculate the gain, that is 1 plus RF by Ri. this gain will convert it into decibel. Later on, by making use of a semi-log paper, we will draw the frequency versus the gain in decibel to get the frequency response of non-inverting input terminal. Now we will connect these two circuits on the breadboard and we will verify for the output waveforms. You try with the different values of the frequencies, note down the output voltage, then calculate the gain and gain in decibel and try to draw the frequency response on semi-log paper. Now this is the circuit of inverting amplifier. This is the op-amp IC741. I hope it is clear, the notch. With this notch we will start the pin numbers 1, 2, 3, 4, other side 5, 6, 7, 8. So it is a 8 pin IC. Pin number 2 is connected, you can see one resistance is connected, and at the other end it is given to the signal generator. You can see signal generator is connected to the resistor and resistor other end is connected to pin number 2. The red wire, pin number 3, is connected to ground directly. Pin number 7 is connected to plus VCC of dual power supply. Pin number 4 is connected to pin minus 12 of the dual power supply. Also the common is connected to the ground. Okay. Now, and one more resistance, that is the feedback resistance, is connected between pin number 6 and pin number 2. So at start, to just check the output waveforms, I have set the frequency of 1 kHz and input is around 1.12 volt peak to peak. Pin number 6 is connected to the CRO output and this is connected to pin number 2, that is the input is connected. Pin number 6 to this channel 2 of the DSO. Now I will turn on this. Now this is my input, which is, you can see, I will set it. Okay, you can see here the input starts with this point and as it is a sine wave, it is like this. Now as per our discussion, the output should be 180 degree out of phase with respect to input. So I should get the waveform in the opposite direction as it is available now. I will just turn on. I am rearranging it. Yes, you can see here, if I check for yellow line, from 0 it is incrementing, reaching maximum value, coming down at pi, then at 2 pi again it is coming to the 0 degree. But blue line, you can see it is inverted as compared to the input. So there is a 180 degree phase shift with between input and output waveforms. So next we will set one voltage value here. So now the value is 1.12 volt peak to peak. Okay, I will keep it as it is, you will note down it, and frequency I will drop it to around 500 Hertz. Okay, it is near to 500 Hertz. At this 500 Hertz, I will note what is the output voltage. So output voltage, I will note the second one, the second signal, and you can see the output voltage is around 539 millivolt. Just change the frequency to 1.5K So it is near to 1.4 kilohertz. You can see the output voltage is around, still it is same, 536 millivolt. Similarly, you go on incrementing the frequency. I'll go to 5 kilohertz. So it is near to 5 kilohertz. You can see the output voltage is around 540 millivolt. Okay, we are not measuring this V average, we are noting down the VPP. Okay, so 10 volt. So it remains a 10 volt for first few frequency, and when I increase the frequency further more, so I'll just tell you what is the frequency. Now the frequency is around 17 kilohertz, and you can see there is a drop in voltage. It is now 9.80. Similarly, when I increment the frequency furthermore, now it is around 26 kilohertz. Now the output voltage is 8.6 volts. Okay. Similarly, with increment in the frequency, the output voltage goes on reducing. So you need to note down what is the frequency and what is the output voltage, and input voltage is fixed, that is 1.12, and you have to calculate V out by V in, that is gain, convert that gain into in terms of decibel, then you can plot the frequency response on the semi-log paper. Next, we have modified the circuit. You can see the pin at pin number 2 we have connected one resistor, and other end of this is connected to ground directly. At pin number 3, the black wire is input is connected from the signal generator, and remaining things are same for the plus and minus VCC dual power supply. And to check the output, the DSO is already connected at pin number 6. Now I'll set some frequency around 2.15, it is 2.15 kilohertz, and voltage is same as our previous 1.12 volt peak to peak. And you can see on the output, on the DSO, the input waveform. And as per our discussion, for the non-inverting amplifier, there should not be any phase shift. So my output should overlap the input. So this yellow is the input, and now this blue one is the output. You can see the phase shift is 0, and we define the in phase signals as the two signals which reach their 0 and the maximum value at the same time instant. We call them as a in phase signals, or you can say the phase shift between those two signals is 0. Here also, like in inverting amplifier you just go on changing the frequency, note down what is the output voltage here, and calculate the gain, convert it into decibels, and try to draw the frequency response. With this experiment, we verified the two modes of operation of an op amp, namely the inverting mode and the non-inverting mode, and we concluded that in inverting mode the output waveforms are 180 degree out of phase with respect to input, and in non-inverting mode the two waveforms, that is the output voltage and the input voltage, are in phase. Thank you.